Hello and welcome back. Today is a big day. We are going to use derivatives to find where a graph is increasing or decreasing. And y'all, it's getting real now because we're starting to really get into the meat of calculus. How can we find the values of x on the graph of a function where it's increasing, decreasing, or constant without seeing the graph? If f of x is a continuous function, then the derivative can only change signs at a critical value. And if f of x is a discontinuous function, then the derivative could change signs at a critical value or at a discontinuity. Example 1. Here we have a graph. It's defined on -3, 7. List the open intervals over which the function is increasing, decreasing, or constant. So first, where is f increasing? Well, right here. So that's between -3 and -1. Where is it decreasing? Well, that's over there, between 2 and 7. Where is it constant? That's right in the middle there, between -1 and 2. Here's a fun word for you, monotonic. That's if the first derivative never changes sign. Here are some guidelines for finding intervals on which a function is increasing or decreasing. Let f be a continuous function. To find the intervals where it's increasing or decreasing, step 1 would be to find the critical values, including the discontinuities on the interval, and then create a number line chart using these critical numbers. Now, if you're asked to justify your reasoning, the number line chart is not a valid justification. You have to write a clear and concise statement using mathematical language, but the number line chart, that's a way to organize your brain. Choose x values between the critical numbers to test the sign of f prime on your sign chart. For example 2, we're going to find the open intervals on which f of x is increasing and or decreasing and justify. So our function is 2/3 x cubed minus x squared minus 4x plus 2. Step 1 would be to find the derivative. Then we need to set it equal to 0 and start factoring or rearranging to see if we can find the zeros. So I found two zeros, one at -1 and then the other one at 2. Now I make a number line chart. And on that number line, on the top, I'm going to keep track of what the derivative is doing. And on the bottom, I'm going to keep track of what the function itself is doing. And at these up and down little fence post things, I'm going to put my zeros. Then I'm going to create test numbers in between the zeros. So right here, less than -1 would be perhaps -2. So I'm going to come back to my derivative function, and I like using this part here. And if I plug in -2 for all of my x's, we don't care what the actual value is, we just care whether -2 is going to make the derivative positive or negative. So if I put in a -2 right here, I get -2 minus 2, that's negative. If I put in a -2 at x plus 1, I get -2 plus 1, well, that's also a negative. Negative times a negative is a positive. Now let's hop over here and go between -1 and 2. Well, 0 is a good guided track there. So if I put in a 0 for x here, I get a negative number. If I put a 0 for x there, I get a positive number. And negative times positive is negative. finally, let's try something above 2, maybe 3. So again, going over to my derivative, if I put in a 3 here, I get 3 minus 2, that's positive. And 3 plus 1, that's another positive number. So I've got positives there. Now, what is this telling me? When the derivative is positive, my function is increasing. When my derivative is negative, my function is decreasing. And then it's positive again, so it's increasing. So check this out. You can kind of see what the graph is doing, can't you? So to explain all this, I would say f of x increases on negative infinity to negative 1 and 2 to infinity because f prime of x is greater than 0. F of x decreases from negative 1 to 2. It's in the middle here because f prime of x is less than 0. This is actually called the first derivative test, which says let c be a critical number of a function f that's continuous on an open interval. If f is differentiable on the interval, except perhaps at c, then f of c can be classified as following. F prime changes from negative to positive at c, then f of c is a minimum. Okay, negative to positive creates a minimum. Negative to positive. If f prime of x changes from positive to negative, then we have a maximum. So we've got a positive slope to a negative slope. If f prime of x just doesn't change sign, then f of c is neither a relative maximum nor a relative minimum because it's just given the function f of x equals x to the fourth minus 8x squared plus 1, find the open intervals on which f of x is increasing and or decreasing. All right, so first step is to find the derivative and set it equal to 0. Now be careful because when you pull out that 4x, some people like to just divide it out. But don't divide it out because you're going to need it. So from here, we can see we've got 3 zeros, negative 2, 0, and 2. And see that 0 came from that 4x. Now we'll make ourselves a number line chart, putting in our zeros on the little fence posts. On the top, we're keeping track of f prime, and on the bottom, we're keeping track of the graph of f. Now we'll start our little test cases. So if I put in, say, negative 3, I'll have a negative here, and then negative 3 squared, that's 9 minus 4, that's 5. So that's a positive there. Negative times a positive is a negative. Between negative 2 and 0, let's try negative 1. So that would be a negative here, and then 1, that's a negative there. So a negative times a negative is a positive. Let's try putting in just 1. So that'll be positive. And then 1 minus 4, that's negative. So positive times negative is negative. And then finally, let's try 3. So this is positive, and then 9 minus 4, that's a positive again. Positive times positive is positive. So I'm keeping track of f prime on the top. Now, how does that translate into the graph of f? Anytime f prime is negative, f is decreasing. If it's positive, the graph is increasing, then decreasing, then increasing. So once again, we can kind of get an idea of what the graph might look like. It doesn't always alternate negative, positive, so you do have to always check each interval. Now I can translate that into some lovely sentences. F of x is increasing where f prime of x is greater than 0, so that's those guys. -2 to 0 and 2 to infinity, and then f of x decreases where f prime of x is less than 0. So that's -infinity to -2 and 0 to 2. Part B says, determine the x values of any local extrema of f of x and justify. Well, again, this is where kind of getting an idea of the graph comes in handy, because you can see that we'll have a maximum at x equals 0 because f prime of x changes from positive to negative, and we have two minimums, one at -2 and one at 2, because f prime of x changes from negative to positive. Example 4. Find the exact values of any relative extrema of the function g of x equals 1/2 x minus sine x on the interval from 0 to 2 pi. Be sure you're answering the question that's being asked. Are you looking for the extrema, the y values, or the location where the extrema occurs, the x values? This says find the exact values of any relative extrema. So in this case, we're looking for the y values. First step, of course, is to find the derivative of our function, set it equal to 0, and so we have wherever cosine x is 1/2, we're going to have a 0. So that's going to be pi over 3 or 5 pi over 3, and we'll pop those on our number line, but why do I have 4 fence posts? It's good to keep in mind the endpoints. This is a closed interval, so nothing happens past 0 or past 2 pi. Now we get to do our test cases. So between 0 and pi over 3, let's say there's a pi over 4 there. Let's plug that back in here. Cosine of pi over 4 is √2 over 2. So 1 minus that will give us a negative. Let's try pi over 2. Cosine of pi over 2 is 0, so 1/2 minus 0, that's a positive. We could try 7 pi over 4, which is a cosine of 7 pi over 4 is √2 over 2. That gives me a negative again. Now we know that the graph of g is decreasing, and then increasing, and then decreasing again. So we know that g of x has a relative minimum value. Okay, where did I get pi over 6 minus 3 pi over 2? Well, at this minimum here, if I take pi over 3 and plug it in to my original function, that's what I get, pi over 6 minus √3 over 2. And then the maximum is taking 5 pi over 3 and plugging it into our function. Example 5, find the relative extrema of the function x squared minus 4 to the 2/3, and of course justify. Start by taking the derivative. Using the chain rule, take the derivative of the outside, keep the inside the same, and then take the derivative of the inside. Set that equal to 0. And you might think, oh, here are my zeros. But be careful with this because the negative exponent can be tricky. If we clean that up a bit, what do you notice? I have a 0 on the top, and on the bottom, I have 2 places where the graph is undefined. So I have critical values at -2, 0, and 2, but at 0, I have an actual 0. At -2, I have an undefined derivative, and at 2, I have an undefined derivative. And now we just play the checking game again. If I plug in a -3, I'm going to speed this up, I get a negative value. If I plug in -1, I get a positive value. If I plug in 1, I get a negative value. And if I plug in 3, I get a positive value. So my graph is going down, up, down, up. That's what it looks like. See these critical values? They go doink, doink. At -2 and 2, the derivative is undefined. So f of x has a relative minimum of 0 at x equals -2 and 2 because f prime of x goes from negative to positive. And f of x has a relative max value of the cube root of 16 at x equals 0 because f prime of x goes from positive to negative. Example 6, given g of x equals x squared minus 3 over x minus 2, what are the x coordinates of the relative extrema? Well, we have to find the derivative, and lucky you, this is the quotient rule. So pause the video. Low d high minus high d low all over low low. And there you go. Let's clean that up a little bit. We'll distribute the 2x through and then combine like terms. And then we want to factor the top here to find some zeros. But let's just keep the bottom as it is. Ah, there we go. So it's pretty clear to see some of our critical values here. On the top, we've got zeros of 3 and 1. And on the bottom, we have an undefined spot of 2. So here we go with our picket fence. So 1 is a 0. 2 is a place where the derivative doesn't exist. And 3 is another 0. Plugging in values, if I plug in a 0, I get positive. If I plug in like 1.5 or something, I'll get negative. If I plug in 2.5, I get, oh, negative again. And if I plug in like 4 or something, I get a positive. So this is when I was saying, these don't always just alternate positive, negative, positive, negative. You got to be careful to check because we're going increasing, decreasing, decreasing some more, and increasing again. So my graph's going up and then down and then up again. So we have a relative maximum at x equals 1 and a relative minimum at x equals 3. This is kind of fun because now we're going to change it up a little bit and you get to draw. For each statement below, sketch a function that represents the result of the first derivative test for a continuous function f of x with a critical number at x equals c. A, f of x has an absolute minimum at x equals c because f prime of x changes from negative to positive at x equals c. So if f prime of x changes from negative to positive, you know the graph is decreasing and then increasing. There's a lot of different sketches you could put. Here's mine. B says f of x has an absolute maximum at x equals c because f prime of x changes from positive to negative. So it's going to be increasing and then decreasing. So there's my sketch. Let's get a little bit more complicated. F of x has no local extrema because f prime of x is always greater than 0. It's always increasing for all positive x. It's strictly monotonic. It's always increasing. And then D, since f prime of x is negative immediately on either side of x equals c, the function f of x has neither a local maximum nor a local minimum. So it's decreasing on either side of x equals c, but perhaps at x equals c, it kind of stalls out a little bit. So that's an introduction into graph sketching. And like I said, we're really getting into some of the meat of calculus. So thank you for hanging in there with me.